Hello mates, thank you for joining us today. Today I am going to discuss the magnetic field mapping of undulators using Hall sensors. In this presentation, we'll explore the crucial role of undulators in synchrotron light source and the importance of precise magnetic field control for optimal performance. By the end of this presentation, we will gain a deeper understanding of the function of undulators in synchrotron light sources, the significance of magnetic field mapping for undulator performances, and the principle of Hall sensors and their application in magnetic field measurements. So let's begin with the introduction. What is magnetic field mapping? Magnetic field mapping basically is a scientific technique which is employed to visualize and quantify the strength and the direction of magnetic field across a designated region. For example, we get across a synchrotron light source. What is that? Scientists use these synchrotron light source devices called undulators to generate intense tunable X-rays for various research applications. These undulators rely on precise controlled magnetic fields to function properly. So magnetic field mapping of undulators is a process of measuring the direction and strength of the magnetic field across the entire undulator. So you must be thinking of what is undulator. Undulator are basically specialized components that are found in synchrotron light source. These are essential arrays of permanent magnets arranged to generate a specific kind of magnetic field. These magnetic fields play a crucial role in shaping the properties of light emitted by the synchrotron. These can be permanent or superconducting magnets. Electrons traversing the periodic magnetic structure are forced to undergo oscillation and thus to radiate energy, because we know that accelerated charged particle emits radiation. These radiation produced in an undulator is very intense and concentrated in narrow energy bonds in the spectrum. It also culminates on the orbit plane of electron. We define a term called undulator strength parameter, that is K equals to EV lambda by 2 pi mc, where lambda is the spatial period of the undulator magnets, m is the electron rest mass, b is the magnetic field, and c is the speed of light. Speaking about magnetic field of undulator, undulator magnetic field plays a very crucial role in generation of synchrotron radiation. Understanding the magnetic field distribution is essential for improving the performance of undulators in various scientific applications. Undulators can provide several orders of magnitude high flux than a simple bending magnet, and such in high demand at synchrotron radiation facilities. For an undulator with n periods, the brightness can be up to n square more than a bending magnet. The first factor of n square occurs because the intensity is enhanced by a factor of n at harmonic wavelengths due to constructive interference of the field emitted during the n radiation periods. The usual pulse is a sine envelope with some envelope. The second factor of n square comes from the reduction of emission angle associated with these harmonics, which is reduced as 1 by n. When the electrons come with half the period, they interfere destructively. The undulator stays dark in that region, so the same is true if they come as a beat chain. This is a diagrammatically presentation of undulator, where the series of magnets are placed, very strong magnets or superconducting magnets, where the direction of dipoles are changed periodically. The electron beam, you can see the electron beam entering through the upper left region mentioned as 2, and you can see the synchrotron radiation coming out from the third region. As we discussed magnetic field, magnetic field and mapping of magnetic field in undulators, what is the importance? What is the importance for that? So in synchrotron facilities, undulators rely on precisely controlled and uniform magnetic fields to function properly. Magnetic field mapping is essential for undulators because of several critical reasons, such as ensuring very optimal performance, quality control and error detection, maintaining beam stability and reproducibility. Without proper magnetic field mapping, undulator performance can be compromised, leading to unreliable and potentially potentially unstable X-ray beams for critical research purposes. For mapping the undulating magnetic field, we generally use the Hall sensors. So before discussing what is Hall mappers, we'll first know what is Hall effect. So Hall effect is a physical phenomenon which is described as the transverse electric field that develops in a conductor when it carries an electric current and is placed in a perpendicular magnetic field to the region of flowing of current. So the schematic diagram you can see, the current is exiting from this direction, and the magnetic field is perpendicular to the region of flowing of current. So the electrons and charged particles, they experience a force due to Lorentz force, and with time the potential, with time the force, the electric field generated due to accumulation of charged particles becomes equal to the electric field that we apply, and that is known as Hall voltage. Formula for Hall voltage is Vh equals to Ib upon Ned, where N is equals to density of electrons, mobile charges, and E is the electron charge. The Hall effect can be used to measure magnetic fields with a Hall probe. So high precision Hall sensors are utilized for mapping the magnetic fields in undulators. These sensors provide accurate measurements of the magnetic field strength and direction, enabling detailed analysis of undulators' magnetic properties. So as we studied about the Hall effect, now we'll study what is Hall effect sensor, like how it works. Basically, Hall effect sensor is a transducer that varies its output voltage in response to a magnetic field. They are basically used for proximity switching, positioning, and current sensing applications. And what is the working principle of Hall effect sensors? This basically they consist of a thin piece of rectangular p-type semiconductor material such as gallium arsenide, indium stibnite, or indium arsenide, passing a continuous current through itself. When the device is placed within a magnetic field, the magnetic flux exerts a force on the semiconducting material which deflects the charge carriers, electrons, and holes to either side of the semiconductor slab. The movement of charge carriers is a result of the magnetic force they experience while passing through the semiconductor material due to Lorentz force. As these electrons and holes move sidewards, a potential difference is produced between the two sides of the semiconducting material by the buildup of these charge carriers, by the accumulation of these charge carriers. Then the movement of electrons through the semiconducting material is affected by the presence of external magnetic field, which is at right angle to it, and its effect is greater in a flat rectangular shaped material. You can see the diagram. The effect of generating a measurable voltage by using a magnetic field is called the Hall effect that we studied. So to generate a potential difference across the device, the magnetic flux lines must be perpendicular to the flow of current and be of the correct polarity, generating a south pole. Also, the Hall effects are available with either linear or digital outputs. The output signal for linear sensor is taken directly from the output of the operational amplifier, with the output voltage being directly proportional to the magnetic field passing through the Hall sensor. The Hall voltage is given by this formula Vh equals to Rh into I upon T into V, where Vh is the Hall voltage measured in volts, Rh is the Hall effect coefficient, I is the current flowed through the sensor in amperes, T is the thickness of the sensor in millimeter, and B is the magnetic flux density in Tesla. So as we studied about Hall sensors, now we'll get to know what is Hall mapping and how we do Hall mapping. The experimental setup that involves the precise positioning of Hall sensors along the undulator structure is known as Hall mapper. By systematically scanning the sensors, a comprehensive map of the magnetic field distribution is obtained, facilitating in-depth analysis and optimization. To build a Hall mapper, we need 3-axis Hall sensors. Generally, we can use a commercially available 3-axis Hall magnetometer or a sensor array, which allows all 3 components of the magnetic field to be measured simultaneously. Positioning jet. This is almost always a custom designed mechanical arm that allows a systematic scan of the volume of interest. The third thing is temperature control. These are 3 basic approaches to dealing with the temperature sensitivity of Hall sensors. Air condition the room, either use Hall probes enclosed in a temperature controlled oven, or measure the sensor temperature and correct the measurements using calibration data. Out of that, we use Hall probes that are enclosed in a temperature controlled oven. The output of Hall mapping system is very much straightforward. Three components of magnetic field vector we get from that Hall mapper, which is measured with low precision and very high accuracy and sampled at points throughout the volume of interest of region. Since here, Hall mappers have found widespread use for characterizing insertion devices such as undulators for synchrotron light sources. Throughout the world, dozens of such facilities are now in operation, like Laboratoire National de Luz Synchrotron and LNLS, National Laboratory of Synchrotron Light, that is in Brazil. You can see the figure of the setup of that LNLS laboratory in Brazil. That is one of the very first such facilities in the developing world. So now we conclude our discussion for today's presentation. The precision, we got to know that the precision mapping of undulator magnetic field in using Hall sensor is very essential for optimizing the performance of undulators for various scientific applications. This study also contributes to the advancement of synchrotron light sources and free electron lasers by providing valuable insights to the magnetic field distribution. Thank you. If you have any query, feel free to ask me on the mentioned email account. Thank you.